I think we can get started. Thanks everyone for coming to this week's NPA seminar. We have Jihee here. She did her undergrad studies in astronomy actually at University, then University of Utah for her PhD, where I believe continued to work in astronomy, and then started a postdoc at Argonne working on the EIC, I think more on the detector hardware side of things. He's now doing her second postdoc at BNL, working with Thomas, who some of you know, on also EIC studies, but more on the physics analysis side of things, and also started working on STAR recently as well. Yes. So yeah, without further ado, take it away to tell us about the second detector opportunities at EIC.
Yeah, thank you for the introduction. Hi, everyone. I'm really happy to be here to give my first EIC talk. And then I also looking forward to get to know everyone later today and then tomorrow. So today I will be talking about the Electron-Ion Collider, the second detector program at the BNL. So this is the outline of my talk. So with the introduction, I will talk about the EIC in general, and then move on to the second detector, the physics-focused measurement, and then also ongoing the studies. So let me start off with the HERA facility. So this HERA is also electron-proton collider, like the EIC. But it has a higher the central mass energy, and it has only the polarized electron and then collide with the proton. So it's actually using the golden tool called as a deep elastic scattering, DIS. And then there's a main two scattering experiment called H1 and then JUICE. And then they are actually looking into the internal structure of the protons as well as properties of the quarks. And then this experiment actually build up the foundation for the next generation of the particle physics laboratories, such as LHC. And they also provide very interesting insight into the field. So here, actually, they use the golden process called the DIS, deep elastic scattering. Basically, they're a point like the electron exchange the virtual photon on the target, the proton, try to look into the interior of the proton. So in principle, the quark in the proton-proton collision, it's actually better to study the gluons, because you can actually access directly the quark-quark and the gluon-gluon the interaction. But the DIS, actually, they're the electromagnetic, the process, which is well known. So any like a small deviation from the gluons, actually, it's easily can the measurable. So that's why it's a DIS is actually a golden tool to study the gluon. So here there's two actually the kinematic variables put here. So the Q square is the resolution power. So it's a full momentum transfer from the scattered electron. So there's an incoming and then outgoing electron, and then measure the Q square. And then the other one is called the Buchan X, which is a momentum, the fraction of the nucleon momentum carried by the struck quark. So actually, we are trying to map out or try to interpret the data in the kinematic, the plane of the Buchan X and then the Q square. So from HERA, actually, we learned a very interesting the insight. So here, they actually measure the proton structure function called the F2, which is describes the quark and anti-quark momentum distribution. So here, this figure shows the proton structure function versus the momentum transfer Q square. So if we assume this virtual photon interacts with the point like the quark, then this should be independent of the Q square. So that's called the Newton scaling, the invariance. So if it's at the bottom, as you can see, the measurement is also flat, which is independent of the Q square resolution power. But as we go lower the X, and then you can see there's you can see the slope. So that means the Newton scaling is broken, and then that actually tells now they are interacting with something else, which is the gluons. So that's the word actually telling from this figure. And also, once you know the structure function, actually you can extract the quark and gluon distribution. So parton the function PDF. So here, the left figure shows the parton density distribution versus the X, the fraction of momentum, nuclear momentum carried by the struck quark. And then as you can see, the lower X region, there's the gluon density actually dramatically increased. So this means the proton is almost entirely the gluon and the C quarks below the X 0.3. So this is the where we are actually moving into the higher energy, and then you can access gluon dominate the region. But so we know the proton is, so nearly all the visible matter is made of the proton, quark and gluons. But still there's questions, we only answer partially. Still we are puzzled by the proton mass. So here the left figure shows the actually the sum of the quarks matter mass on the side. The other side is the actually proton mass. So it's only Higgs mechanism only responsible for or explain only 1% of the proton mass. If you're just adding the all quarks, and then also gluon is the massless. And then the right-hand side, actually the quark mass is only the 1%. The rest of it is a gluon energy and the quark energy. So actually proton mass is cannot be described as the mass. So it's actually the quark and gluon dynamics actually make this proton the mass. So we try to investigate or try to know about how they are rise or generate the proton mass. And then there's another puzzle is about the spin, the proton spin. We know that it's one halves. And then this the spin actually have a three component. It's coming from the quark, and then also the gluon, and then also there's a quark and gluon internal the motion, so angular momentum. So on the right hand side, this is actually the DIS data, and then some proton data. So this is actually looking at the gluon the portion as a function of the X. And then this dashed line is where actually the data presented or measured. So it's actually, so the current data actually only explained above the X tend to be minus third. And then that also gives only about like a 40% of the proton spin. And then also the quark spin only accounts for about the 30% at this limited the X range between the 0.05 and 1. So still we don't really add up all the proton the spin. And then we don't know what's actually contributing at the very low the X region. So this is also we are looking at the quark and gluon at the lower X so that we can understand better on the proton mass and then also the spin. So that's the question actually we are trying to answer. But what actually we needed to actually investigate the puzzles? So we actually need very wide center of mass, the energy range, so that we can actually map out the nucleon-nuclei structure from the high and the low, the X, the region. And also we wanted to have polarized electron and then hadron beam so that we can actually access the spin structure. And also it can lead to the 3D spatial and the momentum structure of the nucleon. And then also if we want to look at the gluon density, then nuclear beam actually help. And then also we need a high luminosity with very large, the forward and the backward acceptance so that we can actually map out the 3D structure of the nucleons and the nuclei. So all this component, we can actually try to build the electron-ion collider to meet all the requirements. So the electron-ion collider, so this is going to be the first polarized electron and also polarize the ion collider. And it will be built based on the existing RIC facility. It will be colliding with a proton and then also electron with the proton and then also the nuclei up to the uranium. And then this is also based on the Gordon process, the DIS. And then, so now there's actually detector 1 called the EPIC. It's seated on the where the RIC star currently located, IP6. And then we expected the EIC start up in the early part of 2030, and the RIC operation will be concluded in the 2025, and then transition into the EIC construction the stage. So this is a more detail for the EIC design. So it will have 2 interaction regions. So there's a IP6 and the IP8. There's IP8 is where the S-Phoenix right now it's just sitting there. And then the EIC will have high luminosity. So it's almost 100 more than the Hera. And then it will integrate with the interaction region so that it has a more larger, the forward and the backward acceptance. And then central mass energy range is between the 30 to the 140 GeV. It's lower than the Hera, but this is where the EIC is sitting there. And then they're gonna be using the existing hadron storage ring. And then the energy is 41 and 100 up to 275 GeV. And then they're also trying to have a polarization more than 70% for the light ions. And then also it will be up to the lead and then also radium as well. And then, but they will take out one of the hadron storage ring, and then they're gonna put the new electron, which is a 5 to 18 GeV. And then also they will have a new electron, the rapid cycling synchrotron as well. So this is the EIC, the accelerator, the design. So here I'm showing the kinematic, the range. There's an EP and then the EA. So here I only showing the polarized the experiments only. So it's a Hera is not there. But so this EIC will be the first polarized electron and then polarized the proton. And it will be extended to the EA collisions too. So it's if you look at the yellow band, this is where the EIC will cover the kinematic range. So it has a larger coverage compared to the previous or the current the experiments. And then again, the central mass energy is like between 30 to 140 GeV, and then it will help to access the wide, the X, and then the Q square. And also, if we look at more closely, if you look at the EA collision, then you will get the more lower X. You can access more lower the X region. So the heavier nuclei beam actually help to probe the lower X the region. So this actually the EIC scientific foundation is well built, and then the series of report it's over actually the 2 decades. It will be the unique machine in the next decades, and it try to address, try to answer the what's the proton mass or and then also spin, and then how the gluon and quarks dynamics, they trying to answer those questions. And then actually 2023 long-range plan recommendation says it's the completion of the EIC was the highest priority for the facility construction. So it's really emphasized and recognized in the various the report and then the white paper. Yeah. So what actually like EIC experimental measurement? So here I have showing the 3 elastic scattering event kinematics. So here the first inclusive DIS. So this channel, we actually trying to measure the scattered electron. So it should have a larger kinematic coverage. And then also we need to have a better electron and then hadron, the separation. And then for the middle, this is semi-inclusive DIS. This case, we actually need to measure the scattered electron and then also the hadron as well. So again, this also need a larger acceptance for these particles. And also we need the identification for the hadron part. So these are each actually process need connected to the physics. Actually, I didn't mention it, but the inclusive DIS is actually the part related to the parton distribution in the nucleon and nuclei, and the semi-inclusive DIS actually connected to the spin and the flavor, the structure. And also it's connected to the tomographic transverse momentum distribution. And then lastly, there's an exclusive DIS. This measurement, actually, we need to measure all the particle in the event. So scatter electron, and also there's a vector measurement or the gamma or whatever, the outgoing particle, and also scattered proton or the nuclei. So this, for the exclusive DIS, actually you need a very high luminosity, and also you need to design the machines to actually detect all the particle. So because the scattered electron gonna be detected in the central detector, and then also vector measurement, but it's a scattered proton or nuclei actually very forward. So actually it really depends on the interaction region design. But how we can make a synergy with the current RIG result? So the RIG actually have the polarized proton, and there was a proton-proton or proton the nuclei collision. So proton is a bit more complex structure comparing to the point-like electron, but still, it's actually the gluon can be accessed directly, the quark and the gluon, but it's a different probe. But this is actually very good to have, because we can test and then also separate the interaction dependent dynamics from the intrinsic nuclear properties. And so it's called we can test the universality. So the RIG has their own unique physics program, but when the EIC data and also the RIG data, actually they're gonna provide more the broad the foundation to the deeper understanding in this the field. And also the RIG and then also EIC is well overlapping the phase space. So this is actually gonna make a big synergy with the RIG and then the EIC. So there's a so the EIC so how what is the conceptual the design detector design in the center? So the central part actually we need a large rapidity to cover. So it's about -4 to 4 the coverage in eta, and then we also need to put the tracking and then also the particle identification and then also electromagnetic and then hadronic colorimeters. So here you can see the central detector and then there's an end cap. Thank you. Yeah. Yes, and then so this actually this is the proton beam is coming this way and the electron beam is coming this way. So the scattered electron actually going to this lepton end cap region, and then any hadrons from the nuclear breakup gonna be ended up toward the hadron end cap. So trying to cover this entire the rapidity. And then so also we have this solenoid, maybe it's not here, but and then trying to detect all the finer state the particles. And then along with the central detector, we have this interaction region, the accelerator, the design. So we actually put specialized detector integrate into the region. So the green, there are two interaction regions, the IR6 and the IR8. So this is the central detector, and then there's the hadron beam, and then also the electron beam, and then we actually put the detector along with the beam line so that we can actually detect the other the particle. So this is IR6 and IR8. Actually, the same, the accelerator, the highlights and the challenges, and then also they're gonna have a same luminosity at the IP, and also they're gonna cover the same central mass, the energy. But it's a similar, but it's also different because it has a different blind spot because it has a different the crossing angle. The IR6 will be the detector 1. They have a 25 milliradian between the two beams. And then for the IR8, they will have a little bit bigger, 35 milliradian. So it will have a little bit more difficult to get the acceptance at the higher the rapidity, but it's gonna generate a different, it's gonna have a different the blind spot. And also the IR6, the design trying to focus on the transverse momentum between 0.2 GeV and 1.3 GeV. But the IR8 actually there's a more space so that we actually can put the magnet so that we can actually make a beam narrow focus again, so that this is going to be the complementary design to have a larger the forward acceptance. So it can go down to the transverse momentum to the 0 GeV. But it also comes with the challenges because how the magnet design to fit into the interaction region. So this is the EIC, the first detector, the EPIC. So this is the central detector. There's like a tracker inside, vertex tracker, and then ACL guide. And then also there is the colorimeter. And then also there's an end cap, the lepton end cap, and then the hadron end cap. And also it's extended to the far forward detector, which is trying to detect the particles from the nuclear breakups. So there's a tracker and also colorimeter, and those are along with the beam line, so that it will detect any charge hadron, and then also neutral, the particle, the neutron, and then also photon at the very high, the large forward rapidity. And then also in the backward, for backward region, they have a very low Q square tagger. And then also luminosity, the measurement in this side. So this is all together to work to measure the final state of the particles. So what about the EIC second detector? That's where I'm working on. So the EIC community actually flavors to accommodate the second detector and the also second interaction reason, like Hera did, like more than 2 experiments. And then second detector working group, actually they're trying to prepare the plan and also build a support to have the second IR, the interaction region, and then the detector. So we have a series of the workshop and then the meetings happening so that we can actually exchange about the ideas. And then this is going to be sitting in the IP8. So the general idea is trying to get the general purpose collider detector to support the EIC program. So it's actually a complementarity the detector. So it can have so it will for the cross checks for the scientific discovery and also control of the systematics. So here the plot actually showed the H1 and then juice. They actually measured the cross section versus the Q square, and then this black is actually they're adding those 2 experiment the data to get a very small the error bar. This is actually helping this control that is a systematic. So that's what we are expecting, and also for this second detector. And also we can try different self-detector technologies so that we can mitigate the risk or also potential opportunity, the R&D detector concept too. And also the magnetic field, also we can try it a little bit different. And also we can broaden the physics program or different physics focuses. So that's the main the idea for the motivation for the second detector. So what is the opportunities at the EIC second detector? So again, so this should be the general purpose, the collider detector design along with the EPIC. So to support the full and broad the physics the program. So there's a physics discussion. We actually focus on some specific the Gordon channels, and also we are looking at any possible opportunity toward the facility the upgrade, and also we can optimize overall the sensitivity to the EIC physics. And then also detector part, we can also promoting the new detector ideas. It's already ongoing. There's an EIC related generic detector R&D program at the J Lab. And also this also helps mitigate the risk by doing the technology redundancy. And also this helps about the control of the systematic for the measurement. So here are the BNL group, within the BNL group, the scope. So this is actually physics, the focus, the measurement. So there are we actually also targeting the facility upgrade to have like a positron beam or the photon or the polarized neutron beams. Those are actually can benefit for the EPIC and then also the second detector. But this is actually work with the accelerator, the division. But this is another the opportunity we can actually aim to go. And we are more interested in the secondary focus in the interaction region. This is again, we actually put the additional the magnet in the downstream so that we can actually have another the beam focus so that we can help to increase the forward acceptance. And also there's the fixed target, the idea, so that if this measurement will be complementary to the STAR or LHCb and also ALICE. So those are the one where the BNL group is looking at. Also, there is a golden channel that this is within the second detector community. They have this different golden channel, but our group actually mostly focus on the coherent vector meson production, so that we are more interested in the nuclear the spatial imaging of the nucleon. So there's a several focus concept for the second detector. So the first one is the muon ID. Actually, detector 1 EPI doesn't. There's no dedicated the muon ID detector, but actually you can identify the muon by observing the MIB using the electromagnetic colorimeter and then 8 hadronic colorimeter. But as a complementary to the EPIC, why not a second detector can have actually dedicated the muon ID so that we can actually look at the different decay channels. So the muon, detection of muon actually give a very clean signal compared to the electron channel. And also it reduced ambiguity to the scattered electron. So in the top, the right figure actually show the red is this is the EIC, the J-size simulation. So the red is the signal, and then the open circles are the background. So actually the backward region actually the dominated so that it's hard to it's confused by this scattered electron if you are looking at the electron channel. So actually there's a EIC generic R&D program. There's trying to make a EIC ID, the muon ID technology working on it. This is the KLM style, the scintillator, the plane detector interleaved with the ion plate. But this is actually replaced with the hadronic the colorimeter. And then the second concept is the secondary focus at the far forward region. Actually, this is my analysis actually I'm working on this the concept. So this is actually not the detector design; it's a machine design, but detector can be benefit from this. So it's complementary to the EPIC because it's an enhanced diffractive and the tagging physics the analysis. So additional the magnet to focus the beam so that it's actually same as IP interaction point, so that there's a high probability to detect very low PT particles around like a 45 meter downstream, so that actually we can detect the near beam particles when they actually get out the beam envelope. So, and also that helps also, we can tag the nuclear breakups. And then the third one is the fixed target. So this is actually focused on the high X and then low Q square. So this is going to be the complementary to the class 12, the JLab experiments, and then also the STAR or LACCB, and then ALICE as well. But this, the fixed target is I think people found very interesting. And then, but we need to think about the kinematics of the particle, because it's very different from the one that colliding the beam. So, and then everything's going to be the backward. So this is the STAR, the fixed target, the figure. So we actually did into it. The STAR actually put the gold target inside the beam pipe. And then, but we also we need actually like a full range of the tracking system, and also we have to have a very good the electron hadron separation PID in the backward region, and then also we have a very good the backward calorimeter to actually measure the scattered electron. So that's what we try to think about in terms of the detector, the design. Besides that, there's also a lot of detector, the R&D is going on. You can find that this is actually the last year funded. And then this is the link that you can actually look into it. So this is the annual the proposal opportunity. And then this program actually aimed for the Detector 2 and then also possible upgrade of the Detector 1. So it invites the detector expert and then discuss the concept and then also proposal the review. And the manual technology actually being developed in the program, and then now it's used in the EPIC, and also it will be available for the Detector 2. Yeah. So what actually doing at the BNL? So we are actually focused on the diffractive, the physics program. So this is just a cartoon that I try to describe. So this is a typical the DIS event. So the electron and the photon, there's also breakup or scatter the hadrons. But DIS usually have a lots of tracks, and then it's go everywhere. But the diffractive events actually very clean. You will see only one particle actually generated, and then you will detect the scattered electron and also scattered proton or scatter the nuclei. And then also diffractive events actually characterized by like a detection, like a very forward scattered proton. And then also the vector measure, those are actually within the mid rapidity. So there's a very big, large rapidity gap in the event. And then also it's very clean. So the diffractive events, actually they have a coherent event, which is at the target, the proton stays intact. And also there's incoherent events that target actually breaks up. So both events are actually equally variable. And the coherent actually give a special structure of the gluon, and also incoherent gonna give the fluctuation of this fluctuations. So here I actually here the central detector, you will see the vector meson in the barrel region, and also the scattered electron will be detected in the electron end cap, and then scattered proton will be go forward and then detected by the far forward the detector. And then this actually the T can be reconstructed by this vector meson and also scattered electron and the incoming electron, or if you can actually measure the recoil, the proton or the nuclei, then you can also actually calculate the T. For most of the case, the heavy nuclei, they are actually within the beam envelope, so it's hard to detect. So usually you will get the reconstructed T using the vector measure and then scatter electron. So actually, this diffractive, the concept is more well known in the optics. So if you think about the light plane encounter any obstacle, then it will bend and then make an interference. The pattern, which is shown on the left figure, and then this distance between the minima, those are the one tells like the size of the object. So it's similarly, we can actually see it in the coherent scattering the cross section shown on the right hand side. And then this actually the proportional to the inverse of the target size. So once you can measure the cross section as a function of the T, and then you can actually put into the Fourier transformation, then you will actually get to the gluon distribution in the impact parameter space. So that's how we say the diffractive, the physics actually lead to the spatial, the imaging of the nucleons. But in the real, the experiments, actually we're gonna measure the sum of the coherent and the incoherent process. So here, the low T is actually coherent, is the more dominate, but then the higher T, then this coherent event is varied by the incoherent. So, but measuring the coherent event is very challenging. So what we do is we actually try to tag the nuclear breakups and then beat those the incoherent event. And then so that's the middle plot. That's the actually trying to show how the beetle efficiency in the IP6. And then the right hand side, this is the actually showing how well we can actually observe this coherent diffractive pattern as a very tracking the resolution, in particularly the transverse momentum. And then so we actually trying to look at the coherent, incoherent vector measure production the events. So we actually look at the central tracker and also the colorimeter information so that we can try to reconstruct the T within the central detector information. So the black is this is the electron channel, and the open circles are the T distribution. And then the black dots are the where we use the reconstructed the scatter electron, and then also the vector meson. And then the middle plot is using the muon channel of the J side. But still, we see the hint of the dip, but we actually cannot see the real diffractive the pattern because it actually needs very the scatter electron should be very precise. The tracking the resolution should be very precise. So we actually trying to do the more different tracker design, so like a drip chamber or a TPC, so that we have a more the hits, so that we can actually improve the backward tracking performance, so that we can get a better pattern recognition, and then or also reduce the background. But this is actually very challenging to measure the diffractive pattern using the central tracking and then colorimeter. But maybe we can actually possible to do with the secondary focus. So secondary focus actually improve the forward acceptance in the detector. So you can actually have a access to very low transverse momentum for the proton or the light nuclei. So then you can measure the scattered proton or the nuclei. And then also you can detect the target fragments so that you can actually beat out any breakups, the incoherent process. Also, you can measure all the finer states of the breakups. And then that also lead to, we can also study more heavier nuclei. And then also, we can also have a chance to look at the rare isotopes, the detection. So the right-hand side, this is actually the IP6, the acceptance. So the XL is the scattered proton versus the proton beam energy. It's like a 10%, but then if you add secondary focus, then you will dramatically improve the detection, the acceptance area. It's almost the order of magnitude improvement in the forward the acceptance. So this is the far forward detector, the layout. So here, actually, we have a same the B0 spectrometer, tracker, and then colorimeter, and then also all momentum detector, the tracker, and also the colorimeter. And then we actually put the tracker at the secondary focus. So here, the top, the right figure, this is the 0-degree colorimeter, which is detecting the neutrons. So as you can see, there's we up to the 10 milliradian, and then now it's detected up to the 6 the milliradian. This is almost uniformly. It has also larger forward acceptance compared to the IP6, and then we actually also put the tracker at the secondary focus. Here that we call the Roman concept. So it's a tracker actually around the beam profile. So it's if we make a beam smaller, then you can put the detector more closer to the beam. So that's how we see the impact in the bottom figure. So this is a DVCS, the scattered proton distribution at the tracker, the plane. So this white spot is the where we can actually have the window for the Roman part, the detector. So it's a beam parameter actually makes significant impact how you can detect all the scattered protons. So that actually benefits the larger acceptance in the low PT, and then also reduce the risk to the the nuclear fragments. So here, actually, this is from the Yale report. So if we wanted to actually see the diffractive pattern, then there's the red is the coherent and the event, and then the blue is the incoherent. So how much rejection power needed to actually we can see the diffractive pattern? So the first minima is like 3 times, and then the second is 50, and the third is 400. So this is the rejection power needed to see the diffractive pattern. And then the middle figure, actually, this is using the secondary focus, the design. The black is all the incoherent event. And then when you actually look for any neutron tagged by the 0-degree colorimeter, and then that's showing the blue. And then once you add the Roman part, the tracker at the secondary focus, and they just dramatically reduce into the almost 0. So this is a vetoing power is very significant, and also it's found to be enough to suppress any all the incoherent contribution in all the diffractive minimas. So the vetoing efficiency is more than the 99.9%. And then I will summarize. So the EIC community favors to have the second detector as a complementary. And it also needed for the cross check, and also it control of the systematic, and also it sees a new opportunity. And the EIC second detector will come few years after the EIC detector one starts. So the BNL, actually, we trying to continue exploring the detector technologies, and also try to formulate the preliminary detector requirements and concept. And then also we establish any the advantage having the interaction region different design. And also we are try to write up the yellow report in the next year so that we can include any physics scope and the detector requirements, and then also detector concept and the technology. And then so the going forward within the second detector community, as I heard, the Yale group is already involved in the EPIC in terms of simulation and the detector R&D, and also the design and the prototype, the EPIC detector. And then we also always looking for more input, and then also the participation, the perspective. And here I actually listed the EIC second detector working group, the conveners, and then also we are actually building up the whole software to study the physics cases. Yes, that's all I have.
Thanks, Judy, for the nice overview. Do you have any questions? Parker, go ahead.
So on one of the slides you showed like pulling the statistics from patch one and zeros.
You mean this one?
Yes. Then you comment like, okay, you will improve your errors by 1/√2.
Yes.
But if you have two interaction points, you reduce the luminosity by half also.
Oh, but the EIC design, we're trying to have a same luminosity. That's the key. Yeah.
So I see. So even at two interaction points, you don't lose in anything.
No, same, try to keep the same luminosity. Yes, yeah.
That's it.
Yeah, that's the try to, yeah. Also, they also have this crossing angle, which makes it harder. Because
Yeah, that's why.
yes, it will lose luminosity, but they actually have a crab cavity, which is I have at the end. But they're trying to make it head on, because the crossing angle, then you will have a bunch. It looks like you are not going to have a head on. But if you actually make a kick in the momentum, so that actually at the interaction point, they actually head on collision, so they can keep all the luminosity at the two different interaction regions.
I actually had a follow-up to that on slide 18. In the diagram, it looked like IP8 does have crab cavities, but
Yes,
IP6 does not.
So it should
And
have.
it is something, it's called something else.
No, it should have it, but maybe it's not showing here. It
Yeah,
both
it-
should be.
okay.
Yeah,
That's what I
both
thought,
have
but
us- Yeah, yes,
Okay.
yes,
Okay.
yeah.
So another point just to add, like you were saying, like you were trying to do fixed target with the gold foil and then the electron coming in. Have you thought of doing the other way now, like gold coming onto the gold foil?
I mean, that I. I mean, we were just looking at where the I mean, this is also interesting. I mean, like we don't know where actually putting it. I mean, the star actually put at the beginning of but I don't know how how easy to put it in the target. But it also depends where you actually can put the target. And also, you also need to think about the service of all the detector parts, like where the blind spot or missing the kinematics, right?
Right, but I'm saying if the like your physics motivation even to think in that direction.
Oh,
If you gain anything, that's all.
this is actually more focused on the JLab, the physics. So this is actually not the low X, it's a higher X. Actually, it's looking at the different the kinematic reason, not the yeah.
But I'm saying the detector is so wonderful, right? It has so many features.
Mm.
For a lot of heavy ion physicists, it would be very interesting, right? Because you can create fixed up low energy heavy ion physics, you know? So that can be just add on, or it's like a cherry on top, right?
Yeah. So yeah, that's true, but I'm not really don't know about the heavy ion. Yeah,
So for sure the fixed target is gonna be a foil, because I mean you mentioned the complementary to say the other experiments like LHCb.
yeah.
LHCb uses a gas as their.
Oh yes, I guess. Yeah.
So is there any maybe possibility of there being some smog two like type?
That's also very interesting. Yeah. Because we also think about with the gas and then also polarized gas.
Right.
Then we actually did look into it. Like then you need to have more space, like to right, like make it. But I mean that's also you need to play with.
Sure.
Yeah. But that's also very interesting. Yeah.
Because at JLab, they do fixed target with gas, right?
Yes. Yeah.
And they have electron beam, which is like 11.5 GeV, right?
Mhm.
So with the 18 GeV,
This is
max, yeah, so you can actually stretch your kinematics even to the JLab physics, right? Of course, they would not like it probably.
So I had a question when you were talking about the different deep and elastic scattering processes. So you mentioned that, or at least I guess it said on your slide that the exclusive DIS can't be detected in the main detector, and I think I just missed like why.
So this actually the scatter proton or scatter the nuclei, those are actually very forward. So it will miss. It will actually. It's more than the eta4. So it actually go along the beam line.
I see.
So that those particles will be detected by this beam, the part 4 detector, which is close to the beam line.
I see.
Yeah. So that's why, yeah. To study the exclusive reaction, that you need to actually measure all the particle. Yeah.
Yeah, just
I have a super naive question. So is your electron and your proton or whatever are they coming in at like 180 degrees from each other, or are they?
So it should be the head on.
Okay, it will be.
Yeah, it should be. Yeah.
Okay. Well, I just wanted to clarify that it's confusing myself.
Wait, but you did show that there will be a small angle, right?
Oh, so yes, the beam actually have the angle. I think let me see. I have this.
The correct
21.
angle. You talked about one was 20 something, one was 30 something. I think that's where your question is. Yeah.
Yes, so the beam actually have an angle, but then this crab cavity. Actually, I have this.
Yeah.
Actually, this is a PDF, so you can see
sorry.
it. But the beam actually, like this is the beam bunch. So in the crab cavity, actually pick this bunch so that they actually meet at the head on.
Okay.
Sorry. Yeah. So that's the.
So the,
oriented the beam. Yes. Yeah.
so how, another naive question, how can you get to PT0? Because
I always just assumed you were limited by the beam itself, like can't just stick the detector right in front of it.
So PT0, I think I would say it's almost along the beam, the direction.
Yeah.
But once you have a detector very close to the beam,
Oh, no, like.
you can make it so that you can detect those particles.
Okay, so it's like almost the, okay.
Yeah, almost zero,
Okay.
sorry, yeah, almost
That
zero,
makes
yeah. So that's actually one of the unique feature in the second detector.
The really hot.
Yes, they actually make another beam focus at the downstream so that beam actually very narrow at the interaction region, right, the collide. And then they will have a little, the envelope, we will say like
Yeah.
it'll have a width. And then there's another magnet to focus so that it's actually very small so that now the other scattered particle will be out of the envelope.
Okay,
Yeah.
cool, yeah.
So, yeah.
So I'm curious because when we're building these detectors, probably like the most expensive part is always gonna be the magnet, right? And
Yes.
you're planning on having two of them. So where are the magnets gonna be built from scratch, or are they gonna be inherited from some retired detector?
That's a very hard question. I mean, they have a challenge. I mean, they have a space so that they can actually put the additional magnet so that we can get the benefit, right? But yeah, I cannot really answer. So yeah. But yeah, I don't know. It's maybe related to funding and the other things to design like how they do. Yeah.
What were the two magnetic fields again? What were the magnetic fields?
Oh, it's actually varied. So each. So this is a constant. I mean, this is a dipole. There's a quadrupole. It's all different. So they actually make a trajectory to go to the particle. But yeah, I mean, it depends on the whole magnet. Yeah. It's all different.
On the barrel, was it a solenoid magnet there maybe?
The central region. We were thinking about the 2 Tesla.
Barrel.
Yeah. Yes, barrel. And the epic is a 1.7, but we are actually pushing 2.2. I mean, but it's also limited about the how they can make a magnet, right? But yeah.
That will be a new magnet.
Yes, yes, that magnet. Oh, I thought
Yeah.
the other magnet. Oh, yes. Yeah, we're trying to have a higher magnetic field. So yeah. That's But this second detector will be built, a couple years later. So maybe we have more, time to. Yeah.
Oh, I see, Nikolai, you have hand raised, go ahead.
Sorry, first of all, I would like to say sorry because I missed practically all presentation, just connected in last moment. So really just only 2 general, I would say, questions. First one connected to background.
Are you still speaking, Nikolai? We heard connected to background and then you stopped. He did, yeah, he just muted, but before he wasn't. Nikolai, you're muted.
Okay, just now,
Okay, there he is.
yes. Can you listen to me? Just reload.
We can hear you now, yes.
So really question exactly comparison background condition with detector 1 and detector 2.
Background. So I think it has. You mean the background from the beam, or?
No, really position is different and really beams are coming from different sides, I would say, different conditions. So just most probably you never maybe simulated this one. And really no answer for the moment, but only I would like to concentrate on this very crucial question.
In the
Just for forward, yes.
Yes, but in the current physics, the analysis, we didn't any for the background yet. But yeah,
Mhm. Okay.
yeah, of course, it's important, yes, crucial, yeah, I agree.
Thank you. So my second question, significantly more not so pleasant. At least last maybe 5-6 meetings what I have been connected, maximum connected 20 person. How you are going to improve this one? Especially if detector one all time complains that lack of manpower. Where is men are coming from?
So for the detector two, as far as I know, we actually more attract international collaboration because the current DOE is more only the project detector, which is EPIC. So we are trying to drive more attention from the international collaboration. Yeah. But at the moment, we're trying to make a strong physics program so that people can we can interest to come or work on. Yeah. Yeah, at the moment, detector two group is very small. Yes. Yeah.
Okay, thanks for the question, Nikolai. Thanks, everyone. Oh, was there one more? Go ahead. Yeah, you.
So if you say the magnetic field is larger at the second detector and then you want to go to lower PT, why wouldn't those low PT particles just not reach the far forward detector?
So the lower PT that I was talking about is more far forward, not the central the detector.
But it comes from the interaction region as well, right?
Oh, but those are more the recoil, the proton or nuclei, very heavy and a very high energy particle. So the low energy particle small PT gonna be curly in, so it's hard to detect. But I was talking about more the recoil proton or recoil like a other heavy nuclei to go very far forward region.
Oh, you mean they will have a high PZ, so they will.
Yeah, high PZ. Oh, yes, that's the correct. Yeah.
They will escape the central.
Yeah, they will.
central part.
Yeah, yes. Yeah, those are always go into the very far forward. Yeah.
Okay, thanks, Jihee. Let's thank the speaker one more time. And yeah, if anyone has any further questions, I think there are still spots on our schedule you can. So